All right, good morning everyone. My name is Kyle Under, and the article I chose focuses on this concept called armor, and it kind of attacks the idea of memory consistency. So let's start with a little bit of motivation. This is actually the full title of the article, and as you can see from that, we're talking about defending against memory inconsistencies for heterogeneous architectures, which will make more sense later. It's published by ACM in 2015. It's a partnership between Princeton University and NVIDIA Research, and these are the authors for completeness. So ARMOR is actually an acronym. It stands for Architecture Independent Memory Ordering Requirement. Since it's kind of defending, it's called ARMOR, which is kind of creative. And this is kind of graphic shows what we're kind of talking about. We're talking about binary translation between one architecture to another. So you can develop code on one machine and deploy it to another machine with confidence. But the concept of general computing really isn't that new of an idea, so what actually is new here? The idea here is where we're talking about parallel processing, specifically with store commands and store load commands from one architecture to another. And this attacks the assumption that developers usually make that parallel code is written as if it's executed sequentially. And so we're kind of trying to get lower level with this and really understand how this is going to interact on different architectures. So this is fine for high level to make this assumption, but it's an interesting challenge for compilers, especially when you move to different architectures. So how do they actually implement this? They start by having two different case studies on two different extremes that you can go with this. The first is the one-to-one extreme that they call it, and this is where you just assume that every command is mapped directly to its applicable counterpart from one architecture to another. So the move command on x86, we just assume it's the same as the store word command on the PowerPC, which is a very naive and wrong thing to do because they could take different clock cycles, and so this ignores all potential hazards in the system, and you can have no confidence in your output. So that's not really a good option. What's the other option? The other option is an overcautious example where you actually synchronize every command after it happens. So processor 1 and processor 2 can actually be independent, but you require them to sync up every single cycle. And so all benefits of multi-threading are gone, so why not just write your program sequentially with this? So this is where the ARMOR idea comes in, and it's kind of like a happy medium between these two. And this is the concept called a MOST that ARMOR implements, called a Memory Ordering Specific Table. And this is how you can map from one consistency model to another. So from x86 to PowerPC, we'll have a MOST. And so this is kind of a hierarchy ordering for different commands from one architecture to another. So a store command can have this hierarchy, store load has this hierarchy, and other commands, they can either be ordered or unordered. And this is kind of how the system will look at this binary translation. And to actually do this, they use a vehicle called a shim to identify the source and destination using the shim, and they'll create the MOST. So this is how the MOST is created, and the MOST is what implements this ARMOR idea. So there are a couple details that go with the shim. The first is cumulativity. So it's a way of grouping commands before and after synchronization commands. So there's A cumulativity and B cumulativity in this example here. So the store word and the load command is before the sync, so this is A cumulative, and this is B cumulative. And this allows some concept called partition refinement, so that it can allow the compiler to really hone in on a small set of commands, optimize those. If it optimizes those, it'll be able to actually ensure the execution through the MOST. So this partition refinement is really powerful due to comparison operators. So it's necessary for these comparison operators to do source to destination moves, because on one architecture there could be a different strictness requirement and it could be different on the other architecture. And so comparison is defined by checking whether one is implied by the other. So if on one architecture you have a single copy atomic command, and the other architecture you have a multiple copy atomic command, the single copy atomic is stricter than the multiple copy, so in the MOST table for that destination move, you'll have a single copy atomic for that command. So this is kind of the theory behind the ARMOR architecture. In the article, they didn't necessarily go through a specific implementation, just kind of more the idea. So this is kind of the idea for binary translation for parallel processing systems. Thank you for your time. Can I answer any questions?
All right, thank you.
Thanks.